Our lesson today is to be able to read numbers in scientific notation, write numbers in scientific notation, and to be able to take numbers in scientific notation and write them in standard form. First, let's talk about what scientific notation is. Scientific notation is a way or a method of writing very large numbers or very small numbers. All right? A number is written in scientific notation when it is represented as the product of a factor and a power of 10. The factor must be greater than or equal to 1 and less than 10. So here's an example, right? Notice first that we're writing the number written as a product, right? So we see a multiplication sign. That number is being written as the product of two factors. The first factor is a number that is greater than or equal to 1 but less than 10. The second factor is a power of 10. Right? Those two characteristics must be in place in order for a number to meet the definition of scientific notation. All right? If the exponent is negative, move the decimal point to the left if we're writing the number in standard form, and if the exponent is positive, move the decimal point to the right if we're writing the number in standard form. Okay, now let's take a look at this next example. We want to be able to identify if the number is written in scientific notation or not. All right, so we have 5.9 times 10 to the negative 6. First of all, it is a number written as the product of two factors. The first factor, 5.9, is a number that is less than or equal to 1, but is greater than or equal to 1 but less than 10. The second factor is a power of 10. So yes, this is an example of a number that's written in scientific notation. The factor is greater than or equal to 1 and less than 10. The power of 10 has an integer exponent, so the number is written in scientific notation. Whereas this next example, right, this next number is not written in scientific notation. Right? Notice it is a number written in as the product of two factors. Yes, one of the factors is a power of 10. But that first factor is not greater than or equal to 1, right? It's less than 1, and that's why that number would not meet the definition of scientific notation. If we want to write the numbers in standard form from scientific notation, here we have 3.22 times 10 to the negative 4. We want to write that number in standard form. When we write the number in standard form, if the exponent is negative, we move the decimal point the exponent number of places to the left. So we write 3.22 and we move the decimal point 1, 2, 3, 4 places left, and we have 0.000322. All right. If we have a positive exponent and we want to write that number in standard form, we move the decimal point to the right. So we start with the 7.9 and we move the decimal point 5 places. 1, 2, 3, 4, 5, and we get 790,000. So let's play around with some of these examples. All right, let's go here. Wrong pen. Okay, is this first number written in scientific notation? Is it a product of two factors? Yes, it is. Is one of the factors a power of 10? Yes. Is the other factor greater than or equal to 1 but less than 10? And the answer is no. So this is not a number written in scientific notation because the first factor, 12, right, is greater than 10. So this would be a no. We want to write these numbers in standard form. So I take 6. Because I have a positive exponent, I have to move the decimal point 7 places to the right. Well, 6 has no decimal point, so we have to start by putting a decimal point in the back of the number, and then we move the decimal point 5 places to the right because the exponent is positive. So I move 1, 2, 3, 4, 5, 6, 7. Right? And each of those places, right, I have to place hold with a 0, comma here, and we have 60 million is the same as 6 times 10 to the 7th power. Here's our next example, 9.9 times 10 to the negative 5. So I start with my 9.9, but because my exponent is negative, right, I have to move my decimal point to the left. So I start here, there is a decimal point, and I move 1 place, 2 places, 3 places, 4 places, 5 places to the left, that's where my decimal point is going to go. I have to fill in those other places with zeros. So we have 0.000099. So what's that? 99 tens, hundreds, thousands, 10,000, 100,000, 99 millions. All right. Next example, we have a positive exponent, 1.285 times 10 to the 4th power. We want to write that in standard form. So we're going to be moving the decimal point 4 places to the right because the exponent's positive. 1, 2, 3, 4. Going to have to add a 0. So we have 12,850 would be 1.285 times 10 to the 4th in standard form. All right. Try a couple more of these. Here we have 7.42 times 10 to the 5th power, but the exponent's positive, so we're going to be moving the decimal point to the right. 5 places. Here's 1 place, here's 2 places, here's 3, here's 4, here's 5. All right, we fill those missing place values with 0, and we wind up with 742,000. Here we have 6.1 times 10 to the negative 2. The exponent's negative, so we're going to be moving the decimal point to the left 2 places. Here's 1 place, 2 places. I have to fill in a 0. Decimal point, we have 0.061 or 61 thousandths. Here we have 3.714 times 10 to the 2nd power. Right? Power of 10 is positive, so we're going to be moving that decimal point 2 places to the right. 1, 2, and we get 371 and 4/10. Okay. Now when we compare numbers in scientific notation, all right, let's see what we have here. An object with a lesser density than water will float. An object with a greater density than water will sink. Use each given density in kilograms per cubic meter to explain what happens when you place a brick and an apple in water. All right, well, if anything is going to sink, you'd think it was the brick. But here what we want to do is we want to take each of these numbers written in scientific notation and write them in standard form. All right, so 1 times 10 to the 3rd, we're going to move that decimal point 1, 2, 3 places. So that becomes 1,000. Right, and this is kilograms per cubic meter. Here we move the decimal point 1, 2, 3 places. So that's 1,840. Here we move the decimal point 2 places, right? So that's 641, right? And that's what we see down here. Because 1840 is more than 1,000, right? The brick's going to sink. Because the apple is 641, was that, what did they say, kilograms per cubic meter. It is less dense than water, so that is going to float. Okay, let's look at this next problem. Some of the top U.S. cities visited by overseas travelers are shown in the table. Order the cities according to the number of visitors from least to greatest. Well, from least to greatest, right, if we're ordering them, I know that times 10 to the 5th, right, is smaller than times 10 to the 6th. So if I look at these two numbers here, right, Boston looks like that's going to be least, and then Metro DC. Okay, and then I see times 10 to the 6th, they're going to be greater. Las Vegas is less than Los Angeles. So you could do the problem that way. You know, start with the smaller powers, and then look at the decimals or the other factor of the smaller powers. Right, so 7.21 Boston. Right, that's going to be less. Right, because 10 to the 5th power is smaller. And then we'd have Metro DC, right? And then we'd look at the 10 to the 6th power numbers, which are going to be larger than 10 to the 5th. We'd look at their other factors. 1.3 is less than 2.2, so Vegas, right, would be next. And then we'd have LA would be the greatest. But the other thing to do is just to write everything in standard form and compare the numbers. So Boston, we have 7.21 times 10 to the 5th. 7.21 times 10 to the 5th, 1, 2, 3, 4, 5, and add 3 zeros. So that's going to be 721,000 for Boston. For DC, change colors here, we have 9, 9.01 times 10 to the 5th, right? So that's going to be, oops, let's undo that, right? We have the 9.01 times 10 to the 5th, so that's going to be 1, 2, 3, 4, 5. That's going to be what? 901,000. Then we have Vegas. Vegas is 1.3 times 10 to the 6, so we take our 1.3, and it's got to go 6 places. 1, 2, 3, 4, 5, 6, 0, 0, 0, 0, 0. So that's going to be what? 1.3 million. 1,300,000. And then Los Angeles, right, that's going to be the greatest. We start with our 9.01. Oops, wrong one. Right, Los Angeles is 2.2. That's got to go 6 places. 1, 2, 3, 4, 5, 6, 0, 0, 0, 0, 0. And that's going to be what? 2.2 million, or 2,200,000 would be the greatest. So if we're ordering from least to greatest, we could just use the numbers written in scientific notation. You'd start with the smaller powers of 10 first, and then look at the other factor. Right, 7.21 is less than 9.01, so that's going to be the smallest. And then we look at the greater factors, and order them from least to greatest as well. Or we could just write the numbers in standard form and list the numbers from least to greatest that way. All right. Here's another example. Writing large numbers using scientific notation. So we take Google purchase YouTube for $1,650,000,000. Write this number in scientific notation. Well, if I have a very large number like that and I have to write it in scientific notation, we know the decimal point has to go here, because we need the number to be, one factor to be greater than or equal to 1 but less than 10. And where would we have to locate that decimal point in order for the number to be greater than or equal to 1 but less than 10? Well, the decimal point's got to be located here. And then we see, well, how many places did that decimal point have to be moved? And that was 1, 2, 3, 4, 5, 6, 7, 8. It had to be moved 9 places. And because it's a large number, right, that exponent's going to be positive. Okay, so we wound up with 1.65 times 10 to the 9th power. Okay, if we write small numbers, let's move that up a bit using scientific notation. Let's see what example we have here. In 2004, the Indonesian earthquake slowed the rotation of the Earth, making the length of the day, wow, that many seconds, a lot. That's what, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 268 millionths of a second shorter. Write this number in scientific notation. Well, once again, where would we have to locate the decimal point for the number to be greater than or equal to 1 but less than 10? Right? The decimal point would have to be located here between the 2 and the 6. How many places did we have to move the decimal? 1, 2, 3, 4, 5. We had to move it 6 places left. Right? So very small decimals. That exponent's going to be negative. And because we moved it 6 places, it would be 2.68 times 10 to the negative 6. Right, so let's do these examples together. Okay, let's look at the first one. So I look at the number and say, okay, where do I have to locate the decimal so that I have a number that is greater than or equal to 1 but less than 10? I'd have to locate the decimal point here. All right, well, how many places did we move the decimal? Well, the decimal, the imaginary decimal point, is back here. So I had to move it 1, 2, 3, 4 places. So for problem number 1, that's going to be 5 times 10 to the 4th power, writing that number in scientific notation. Problem 2, we have 25, what is that, million. Well, where would we have to locate the decimal point for the number to be greater than or equal to 1 but less than 10? Right, and that would have to be here between the 2 and the 5. How many places did we move that decimal point? 1, 2, 3, 4, 5, 6. We had to move it 7 places. So that would be 2.5 times 10 to the 7th power. Right, 683. Where would we have to locate the decimal point so that we have a number that is greater than or equal to 1 but less than 10? It's got to be here. Right? How many places do we move it? 2. So for problem 3, that's going to be 6.83 times 10 to the second power. Right, let's look at 4. Where would we have to locate the decimal point so that we have a number greater than or equal to 1 but less than 10? We'd have to locate it here. How many places did we move it? 3 places. So that's going to be 5 times 10 to the negative 3 power. Remember, small decimals, they're going to have negative exponents. For problem 5, where do we have to locate the decimal point so that we have a number greater than or equal to 1 but less than 10? It's got to be located between the 3's. How many places do we have to move that decimal point to locate it there? 1, 2, 3, 4, 5, 6, 7 places. So for problem 5 in scientific notation, that's 3.3 times 10 to the negative 7 power. And then problem 6, where would we have to locate the decimal point to have a number that is greater than or equal to 1 but less than 10? It's going to have to be located here. How many places do we move the decimal point? 1, 2, 3, 4 places. So that's 5.06 times 10 to the negative 4th power. All right. Okay, we'll finish this off with a few more. All right. Yeah, this will be our last page here. So if you want to try this, writing this number in scientific notation, all right, where would we have to locate the decimal point? Decimal point would have to be located here. How many places do we have to move it? 1, 2, 3, 4, 5. We have to move it 6 places. So that'd be 3.725, right? Don't forget all these other digits, they're important. Times 10 to the, what did we say? 1, 2, 3, 4, 5 times 10 to the 6th power. Right, this next one, where would we have to locate the decimal point, right? To have a number greater than or equal to 1 but less than 10, right? Here. How many places do we have to move it? 1, 2, 3, 4. So that's 3.16 times 10 to the negative 4 power. All right. Last couple of problems here. Oof, it's a big number, 14,140,000. We'd have to put the decimal point here. 1, 2, 3, 4, 5, 6, 7 places. 1.414 times 10 to the 7th power. Here, let's see, decimal point would have to go here. So that's 1, 2, 3. So that's 8.76 times 10 to the 3rd, negative 3rd power. And then finally, right, we only have to move it 1 place, so that's 1.14 times 10 to the negative 1 power. All right, so I hope that's been helpful, and good luck.